Okay, we'll get back to 4.7. We're talking about optimization problems, and in all of these problems we're either going to be maximizing or minimizing a function. In the previous video we did problems 1 and 2. Okay, so let's take a look at problem 3 here next. Problem 3, find the dimensions that will minimize the cost of metal to manufacture a 12-ounce pop can. Note 12 ounces is the same as 360 cubic centimeters. Okay, so this would be a real-life problem that a company would want to know. You're producing cans. You don't want to be throwing money away in manufacturing the cans, right? So what is the minimum cost of metal? Like, how should the can look if we want the cost going towards the metal to be as small as it possibly could be? Should the can be more like longer top to bottom? I don't know. Sometimes you see like the Red Bull cans are longer top to bottom compared to like an ordinary 12-ounce pop can. Or maybe should it be more flattened? Can you imagine drinking out of that? Okay, well, in any case, we're going to have a cylinder, okay, where the radius of the circular base is r and the height of the cylinder is h, right? We're representing a pop can there. And we want to minimize the cost of the metal, so we want to minimize the surface area of the cylinder. Now, the surface area of the cylinder would be the total area wrapping around forming the can here. Okay, I've got the circular top and bottom area of a circle is pi r squared. Okay, so I'm going to have 2 pi r squared, and then plus the part that's wrapping around is going to be a rectangle. The rectangle would have a width of h, whatever the height is, and then the length would be whatever the circumference of the circle would be. The circumference of any circle is 2 pi times the radius. So the area of that rectangle wrapping around forming the can would be 2 pi r h. Okay, and that would be just the general formula then for surface area of a cylinder. Now, I'm going to be minimizing the surface area as a function of the radius. And I would like the function to be only in terms of r. Okay, now they told me that this is a 12-ounce pop can. Okay, there's 360 cubic centimeters in 12 ounces. Now, the volume is what's given here, 360 cubic centimeters. The volume of any cylinder is where you take the area of the circular base and then multiply by the height. Okay, and like I said, that number, 360 cubic centimeters, is given to us. So if we solve for h, divide by pi r squared, h would be 360 divided by pi r squared. And in my surface area formula here, where I see h, I'm going to go ahead and replace that with 360 divided by pi r squared. That way everything is in terms of r. We simplify, okay, pi is going to cancel there. 2 times 360 is 720. R would cancel with one of the r's in the denominator. Now, what are the conditions on the variable? This is something that I'm going to be looking for when I grade a problem like this. Tell me what we know about x or r, whatever the variable is. That will be worth points in the problem. The reason why that's important is because that tells us what the plan is going to be moving forward. Okay, if we're going to be using techniques from section 4.1, which is what these two problems involve, since I had a closed interval, and or are we going to be using techniques from section 4.3? Okay, because 4.3 was all about local maxes and mins, not absolute maxes and mins. That was 4.1. Well, in this problem here, what do we know about r? R can't be a negative, right? That doesn't make any sense. We're talking about radius of a can. R can't be 0, right? Because I can't divide by 0. So the only thing I really know about r is that r is positive. Now, I suppose that I could get an upper bound for r, but I can't get a closed interval, though. Okay, since r can't be 0. So at this point, I'd want to recognize that moving forward, I'm going to be using techniques that were shown in section 4.3. Okay, like I'm going to have to find the local min on the graph, and then I'm going to have to show that that is actually an absolute min. Well, let's see. I'm going to have to get my critical number. So here's S prime of R. It's going to be 4 pi r plus the derivative of 720 r to the negative first. That'd be a minus 720 r to the negative second, or minus 720 over r squared, same thing. Okay, and if you solve this equation for r, add 720 over r squared, multiply by r squared, and then divide by 4 pi, then r cubed is equal to 720 divided by 4 pi. Take the cubed root of both sides, and you get r to be the cubed root of 180 over pi. That would be roughly 3.9 centimeters, okay, if you're using decimal form. Now, like I said a moment ago, the plan for this problem is going to be to use the techniques that we learned in section 4.3. Okay, I don't have a closed interval, so it's not plug in the critical number along with endpoints and see what's the biggest or smallest, like I was doing over here. Okay, I'm going to have to use the first derivative test or the second derivative test. Now, for the problems in this section where you have to use the techniques in section 4.3, I don't care if you want to use the first derivative test or the second derivative test, but make sure that you've shown your work for one of those. Okay, because at this point we will have to prove that this is the correct number, because otherwise how do we know that we have a min value? How do we know that we didn't slip up somewhere in the calculation? We're going to have to prove that. Well, I'm going to use the first derivative test here as a proof, and so I've got my table, got increasing or interval, number chosen, value of s prime, and then the conclusion, and the increasing and decreasing test. 3.9 roughly is my only critical number, so I've arranged that on the number line. Of course, r can't be 0, right? R is positive, so I'm going to be starting at 0 to infinity. And I've got my two intervals written. So now I'm going to select a test value in each one of these intervals. Okay, a number between 0 and 3.9 is 1. If I were to plug 1 into the derivative, 4 pi minus 720, 720 is quite a bit bigger than 4 pi, right? So you're going to have some negative number. Here would be the number that you'd get in decimal form. That would indicate that we're decreasing then on that part of the graph. Okay. How about if in a number in the second group here, like if I let x be 6, or excuse me, r be 6. If I plug that into s prime, r is 6, I've got 24 pi minus 720 divided by 36. 720 divided by 36 is 20. Okay, 4 times 6 is 24. 24 pi, that is bigger than 20. Right, so you've got something bigger than 20 minus 20 is going to produce a positive number. It'd actually be 55.4 if you were to check that. Okay, and we're going to be increasing then on that part of the graph. I'm decreasing and then I'm increasing. That produces a local min at r equal 3.9. Okay, so that would be the proof showing that I got the correct number there. Now, we want to find the dimensions that will minimize the cost of the metal. So I know R, let's get H. Well, here's what H is in terms of R, right? And R is the cubed root of 180 over pi, so I'm going to go ahead and replace that in order to determine H. The cubed root of 180 over pi squared would be the same thing as 180 over pi to the 2/3 power. And a 360, that's the same as 2 times 180, right? Pi divided by pi to the 2/3 would be pi to the 1/3. And then I've got 180 to the 2/3 there still. 180 divided by 180 to the 2/3 would be 180 to the 1/3. 180 to the 1/3 divided by pi to the 1/3, that'd be the same as 180 over pi all to the 1/3, or the cubed root of 180 over pi. Now I still got this 2 in front. The cubed root of 180 over pi, that's what we're calling r. So the height should be equal to twice the radius. And I've circled that. That'd be the dimensions that would minimize the cost of metal to produce a 12-ounce pop can. Okay, a couple things. So first of all, twice the radius would be the diameter. Now, I don't know about you, but whenever I look at a pop can, I don't think I've ever seen a pop can where the height and the diameter are the same. At least not a 12-ounce pop can. So why do you think that pop can companies do it like that when it's economically better to have the height and the diameter be the same? Why do we never see that? Well, there's several reasons, okay? Here's a couple that I've listed. The bottom and the top are not cut from square pieces. They're connected to the can, right? If you look at least the bottom of the can is connected, and it's curved, right? You got like an indented part of the at the bottom of the can. The product label would be something else to consider. Maybe the company wants their label to be bigger, or maybe it's more convenient for the hands. Okay, I mean, something to note here is that if the company was only taking into account the metal, then yeah, they'd want the height and the diameter to be the same. But a pop can company is not only considering the cost of metal when they're mass producing an item like that, right? There are lots of other things that get figured into the cost of the item, right? There's the cost of material, there's the overhead cost, there's the distribution cost, there's lots of different costs that all have to be figured in, okay? Maybe a better example that I had thought of, so I just grabbed a can that, I don't know if you can see that maybe, but this looks more like it's a situation where the height and the diameter are about the same, but you're not drinking out of this, or at least I hope not. Okay, so maybe like a can of beans or like a coffee can or like a tomato paste can, that might be a better example where the cost of metal was more figured into the calculation, so anyway, let me just describe some things that I'm looking for when I grade a problem like this, okay? So in these problems, here's what I'm looking for. I'm looking for the function representing the situation, okay? That's going to be worth points. And then you got to tell me what we know about the variable, okay? That is also going to be worth points, okay? Tell me what we know about x or r. If you don't indicate that, then you won't get full credit. Okay. Now that's important to know what's happening with x or r or whatever the variable is, because that information tells us what the plan is going to be going forward as far as proving that we have the correct answer. Okay. And I'm going to want to see the work showing that you have the correct answer. Okay. So if you have a closed interval and a continuous function, like we had here in problems 1 and 2, you're going to be using the techniques that were described in section 4.1. That is just simply where you plug in the critical numbers along with the two endpoints on the interval, and you see which one is the biggest or the smallest, depending on if you're maximizing or minimizing the function. Okay, that is the proof of why you have the number correct. Like what I did here is the proof that 45 is correct and 90 and 0 are not correct. Okay, and I'm going to want to see that. In this other problem, the first derivative test, this is the proof showing that indeed r is a min value. Now in this problem though, I don't know if you've observed it, I said that you're decreasing and then increasing. That means that you have a local min at 3.9. I need to know that that's an absolute min. How do I know that? Well, it's because I only have one min. I'm not comparing that to any other min on the graph. There's only one min. So this local min is also the absolute min. Okay? which means that this test that I did here is the proof showing that indeed I've got the absolute min, because it's a local min and it's the only one, okay? And I'm going to want to see that work. Now I mentioned that you can use either the first derivative test or the second derivative test. I don't care which one. Just make sure that you've used one or the other. If you're using techniques from 4.3, that is, if you don't have a closed interval, you're going to be using techniques that are in 4.3. That is just either the first or second derivative test. Okay. And then of course I'll want to see the answer, okay, and make sure that the units are there. So those are some things that I'll be looking for when I grade your work here on on an assignment. So be sure that that information is shown. Now, in a couple of problems here in this worksheet, I've decided to use the second derivative test. We'll see that. Okay, I could have used the second derivative test here. That wouldn't have been a problem. That'd be fine. Just make sure that you've done that. Okay, use either the first or second derivative test. If you don't have that, you're not going to get full credit then, right?